bias. Exploiting these weaknesses, he gambled profitably for a week before the casino management shuffled the wheels between tables. However, he soon noted various distinguishing features of the individual wheels and was able to follow them between tables, again winning consistently. Eventually, the casino resorted to redistributing the individual partitions between pockets. A popular account, published in 1925, claims he eventually came away with winning £65,000. The success of this endeavor is one possible inspiration for the musical hall song The Man Who Broke the Bank at Monte Carlo, although this is strongly disputed. Statistical analysis. Similar feats have been repeated elsewhere. The noted statistician, Carl Pearson, provided a statistical analysis of roulette data and found it to exhibit substantial systematic bias. However, it appears that his analysis was based on flawed data from unscrupulous scribes. Apparently, he had hired rather lazy journalists to collect the data. Irregularities. In 1947, irregularities were found and exploited by two students, Albert Hibbs and Roy Walford from Chicago University. Following this line of attack, SN Ethier provides statistical framework by which one can test for irregularities in the observed outcome of a roulette wheel. A similar weakness had also been reported in Time magazine on February 12, 1951. In this case, the report described various syndicates of gamblers exploiting determinism in the roulette wheel in the Argentine casino Mar del Plata during 1948. The participants were colorfully described as a Nazi sailor and various fruit hucksters, waiters, and farmers. Using physics and computers. Henry Poincaré. The second type of exploit is more physical, that is deterministic, than purely statistical and has consequently attracted the attention of several mathematicians, physicists, and engineers. One of the first was Henry Poincaré, in his seminal work, Science and Method. While ruminating on the nature of chance, and that a small change in initial condition can lead to a large change in effect, Poincaré illustrated his thinking with the example of a roulette wheel, albeit a slightly different design from the modern version. He observed that a tiny change in initial velocity could change the final resting place of the ball. In his model, there was no ball, such that the wager on an either black or red, as in a modern wheel, the black and red pockets alternate, would correspondingly win or lose. He concluded by arguing that this determinism was not important in the game of roulette, as the variation in initial force was tiny, and for any continuous distribution of initial velocities, the result would be the same, effectively random, with equal probability. He was not concerned with the individual pockets, and he further assumed that the variation in initial velocity required to predict the outcome would be immeasurable. It is while describing the game of roulette that Poincaré introduces the concept of sensitivity to initial conditions, which is now a cornerstone of modern chaos theory. The first roulette computer. A general procedure for predicting the outcome of a roulette spin and an assessment of its utility was described by Edward Thorpe in 1969 publication for the Review of the International Statistical Institute. In this paper, Thorpe describes the two basic methods of prediction. He observes, as others have done later, that by minimizing systematic bias in the wheel, the casinos achieve a mechanical perfection that can then be exploited using deterministic prediction schemes. He describes two deterministic prediction schemes, or rather, two variants on the same scheme. If the roulette wheel is not perfectly level, a tilt of 0.2 degrees was apparently sufficient. We verified that this is indeed more than sufficient. Then, there effectively is a large region of the frame from which the ball will not fall onto the spinning wheel. By studying Las Vegas wheels, he observes this condition is met in approximately 1/3 of wheels. He claims that in such cases it is possible to garner an expectation of plus 15%, which increased to plus 44% with the aid of a pocket-sized computer. Sometime later, Thorpe revealed that his collaborator in the endeavor was Claude Shannon 17, the founding father of information theory. Richard A. Epstein. In his 1967 book, the mathematician Richard A. Epstein describes his earlier, undated experiments with a private roulette wheel. By measuring the angular velocity of the ball relative to the wheel, he was able to predict correctly the half of the wheel into which the ball would fall. Importantly, he noted that the initial velocity, momentum, of the ball was not critical. Moreover, the problem is simply one of predicting when the ball will leave the outer fixed rim, as this will always occur at a fixed velocity. However, a lack of sufficient computing resources meant that his experiments were not done in real time, and certainly not attempted within a casino. The Eudaimons. Subsequent to and inspired by the work of Thorpe and Shannon, another widely described attempt to beat the casinos of Las Vegas was made in 1977 to 1978 by Doane Farmer, Norman Packard, and colleagues, whose team was called the Eudaimons. It is supposed that Thorpe's 1969 paper had let the cat out of the bag regarding profitable betting on roulette. However, despite the assertions of Bayes, Thorpe's paper is not mathematically detailed. There is, in fact, no equations given in the description of roulette. Thorpe is sufficiently detailed to leave the reader in no doubt that the scheme could work, but also vague enough so that one could not replicate his effort without considerable knowledge and skill. Farmer, Packard, and colleagues implemented the system on a 6502 microprocessor hidden in a shoe and proceeded to apply their method to the various casinos of the Las Vegas Strip. The exploits of this group are described in detail in Bayes. The same group of physicists went on to apply their skills to the study of chaotic, dynamical systems and also for profitable trading on the financial markets. In Farmer and Sutterwick's landmark paper on predicting chaotic time series, the authors attribute the inspiration for their work to their earlier efforts to beat the game of roulette. The Ritz Casino attack. Less exalted individuals have also been employing similar schemes, in some cases fairly recently. In 2004, the BBC carried the report of 3 gamblers, described only as a Hungarian woman and 2 Serbian men, arrested by police after winning £1,300,000 at the Ritz Casino in London. The trio had apparently been using a laser scanner and their mobile phones to predict the likely resting place of the ball. Happily for the trio, but not the casino, they were judged to have broken no laws and allowed to keep their winnings. The scheme we describe in Section 2 and implement in Section 3 is certainly compatible with the equipment and results reported in this case. In Section 4, we conclude with some remarks concerning the practicality of applying these methods in a modern casino, and what steps a casino could take, or perhaps have taken, to circumvent these exploits. A preliminary version of these results was presented at a conference in Macau. An independent and much more detailed model of dynamics of the roulette wheel is discussed in Strazzalo et al. Since our primary publication, Private Communication, with several individuals indicates that these methods have now progressed to the point of at least 4 instances of independent insight field trials. Read more about how you can beat roulette with physics, systems, strategies, or even mind control at roulette-bet.com.